Hello, everybody. Welcome to the Biocosmology session, which I am recording live from San Francisco. So the first thing I would like to do is thank the organizers for this wonderful initiative of allowing everybody to participate in a cosmology conference from home. I am going to introduce this new topic that we have heuristically called the birth of a new science. It will actually, I will not claim that this is a new science, but it's just fun to do. So I presented this at SciFu here at Google a couple of weeks ago. So I've left that logo there. What is the talk about? I will claim that we have attempted with my collaborators, Lee, Andrew, and Stu, we have attempted to find a language, a mathematical language between cosmology and biology, and given a value, a quantitative value for the worth of life versus what we call the worth of the cosmos. This is given here in a very basic language, but essentially I will be computing the amount of complexity expressed in the form of microstates, classical microstates. So what we will try to do here is to look at biology from a physics point of view. Of course, biology has been treated many times by physicists. Usually we take approximations and can treat very complex problems like any biological system is. And this time we want to take a very rigorous view as if we were looking at biology with fundamental physics principles. So I can already tell you that we make a very small step in this direction because, of course, it is a very difficult job. How did I start on this, thinking about these? It's because, of course, cosmologists are endowed with the task of counting the number of microstates today because of our problem of initial conditions that we have to solve. And so usually I say that the number of, the problem of initial conditions has been increasing as the decades pass in our discipline. We initially thought it was the number of microstates was given by the microwave background. Then we discovered we accounted for the gravity, and this is dominated by black holes in the middle of galaxies. And of course now we know about the cosmic horizon and the entropy associated with the acceleration of the universe and the number of microstates that comes with that via the Bekenstein bound and inverting the formula for the Boltzmann formula for the entropy. In natural units, then you get this number of microstates, e to the 10 to the 124 microstates for the universe today. And of course, the initial conditions problem will be unlikely. Our conditions are unlikely in one on this large number. And so because of discussions with biologists and the meeting that Lee Smolin and I organized in 2016, I've started thinking that how many microstates does biology correspond to? What does it enclose? So, and realized that, of course, in our counting of microstates in biology, in cosmology, we don't take into account the planet and life. So usually the first answer why one would say that why we don't need to take life into account is because, of course, our planet is tiny, and it doesn't, you cannot have many microstates compared to the Hawking-Bekenstein bound formula, which is very huge, and it is impossible that it would have more power than the number given by the cosmic horizon. And also we don't have a common language to compare microstate by microstate. So this has not been possible to do. Here is where we start looking at the foundations of biology, and in discussions between theoretical physicists and theoretical biologists in our collaboration, we have understood that there essentially are no laws that apply in all systems that we can call, we could even consider to be something like what we have in the Lagrangian of the standard model, that we in principle can derive a lot of cosmology from our underlying Lagrangian that we have in physics. So the only law that we could come up with that in biology is this getting to exist, which gets us nowhere. And Stuart Kauffman, who is a MacArthur Prize, by the way, has developed a formula for describing what happens in biology, which is different from physical systems. So alive systems are different from physical systems. And there's this phenomenon of elements in a system combining themselves and creating a new element. This is described by this equation, combinatorial innovation. This is the equation of the adjacent possible. I will go into more detail if we have a discussion. But essentially, it means that new elementary degrees of freedom keep appearing all the time in biological systems, which we don't have in fundamental physics an equivalent to describe this computation. So with the computation, based essentially on the number of what is the number of atoms that are present in all organic compounds, which are 6. And we let the code run with some variations of that equation. I can go also in more detail in the discussion, and there's more details in the papers as well. But what we found is that going from this start point that you see in this slide, the cosmos has the overwhelming majority of microstates, and our biosphere has none. We've come up with numbers that we found have a name of their own in mathematics. The towers of exponentials are needed to count the number of, let me emphasize, classical microstates that have existed in the biosphere. Because we're doing this with our home computers, we had to stop it at some point when the computer goes in overflow. So essentially, we computed the number of microstates up to the first RNA molecule that is described in biology by the appearance of the RNA world or template synthesis. This is quite interesting, but biologically speaking. The number I give here, 10 to 10 to 10 to 10, is just indicative because it depends on the form of the equation that you choose for the TAP equation, as we call it. But essentially, what is novel is that no matter what type of more biologically sophisticated phenomena we put in, we get a tetration-like numbers much larger than ones given by the cosmic horizon. So, of course, this formula might not be correct, or it's most likely not correct, but it is for us, for Andrew Little, Lee Smolin, Stu Kauffman, and I, who have been looking at getting a description of complex living systems for a long time. Combinatorial innovation, it's probably the closest that we could come up with to describe why is biology so different from physics. And so here is a proposal for a language that could begin to establish a bridge between physics and biology. And in my personal ambition, it would be that physics would grow to encompass new techniques that we can learn as physicists by looking at biology, and start treating almost like enlarging our boundaries of what we call physics, and potentially call biology or simple systems in biology part of physics in the near future. Very interestingly as well, when I've spoken about these in wide audiences, is the fact that our planet is very tiny, but it contains an infinite possibility of microstates, much larger than the whole universe. And I hope that this result can be used as some sort of argument for how our biosphere is valuable, and what is it of a diversity central. The three papers are live on the archive. We have done a press release from Everest Base Camp on April 17th. I think I was live from Everest Base Camp. The papers and the live discussion of the press release are at this webpage, biocosmology.earth, and Andrew will propose a theme discussion on this topic, so that he can also describe the very abundant derivations that he has had to make in order for us to be able to use this formula and adapt it to living systems. Thank you, everybody. I hope this is not more than 18 minutes, but if it is, just cut it, because I've actually not been counting. I am jet lagged. Looking forward to the meeting. Thanks again to all those listening.